Hello, this is Shahin. In this presentation, I'm going to present our work on efficient sampling in POMDPs with Lipschitz bandits for motion planning in continuous spaces. In this work, we use Lipschitz assumption on the rewards of actions in a sampling-based POMDP search tree. POMDP framework is very suitable for formulating decision-making problems under uncertainty. It encodes uncertain and incomplete knowledge not by single states, but by beliefs over all possible states. By optimizing over a sequence of actions and observations, it considers a very large number of possible future outcomes. This comes at the cost of high computational complexity. A POMDP can be solved by performing Monte Carlo tree search. Common approaches are POMCP and Tapir, and they employ upper confidence bound to explore promising actions and exploit good ones. UCB doesn't make any assumption on the outcomes of similar actions. However, many real-world applications operate on compact continuous spaces in which the profile of outcomes are continuously differentiable. Furthermore, the uncertainties present in the environment have a smoothing effect on any discontinuity. Such applications can benefit from Lipschitz assumption on the outcomes of actions. In automated driving, motion planning has to consider uncertain information such as sensor uncertainties, unknown intentions, and future routes of other traffic participants. POMDP framework fits very well for dealing with this problem. Previous works have used POMDPs for this task. However, for being real-time capable, they limited their number of available actions to a very small number, such as 4 or 5. The POMDP framework requires model-based representations on which to operate. We closely follow the models presented by Hupman et al. We use prior map information in our model. As map information, we store a tuple of endpoints consisting of Cartesian coordinates, distance along the path, curvature, and reference velocity. The state S of a vehicle is given by its longitudinal position, velocity, and route. For ego vehicle, the route intention is known in advance, and therefore it is omitted. Observations are defined in Cartesian coordinates and consist of position and speed. We apply path velocity decomposition and hence plan accelerations along a predefined path. Our accelerations are within the comfortable range, ranging from -3 to 1. For predicting accelerations of other vehicles, we use the intelligent driver model. This model consists of a free driving term and an interaction term for avoiding collisions. We saturate the resulting acceleration value with the maximum deceleration and add Gaussian noise to cover for modeling errors and uncertainties in the behavior model. The observation model generates a possible observation from a given particle state. After transformation from path coordinates to Cartesian coordinates, we add observation noise sampled from independent Gaussian distributions. The terms in the reward model resemble those of an ordinary trajectory optimization problem. All terms are modeled as negative rewards. The collision term takes only collisions of the ego vehicle into account. We punish the deviation of the ego vehicle velocity from a predefined reference with an asymmetric loss function. We further punish changes in longitudinal and lateral acceleration. The general multi-end bandit is a sequential decision problem which proceeds in rounds denoted by T. At every round, the agent picks one arm from some set of arms. Its goal is to maximize the rewards it collects over T rounds. The upper confidence bound, the UCB algorithm, is an optimistic algorithm in the face of uncertainty. In each round, the algorithm calculates the index B of A. The algorithm chooses arms at random first, and after k rounds, it picks the arm with the highest index. The UCBV enhances UCB by including estimated variances. In contrast to UCB, the variances of the rewards are not assumed to be equal anymore. Possible algorithm assumes the expected rewards to be Lipschitz continuous and thereby improves the efficiency of sampling by guiding the bandit faster to more rewarding arms. The expected reward function satisfies Lipschitz assumption for any pair of arms and the Lipschitz constant L. The Lipschitz assumption is integrated to the bandit via the confusing rewards and is adjusted by the Lipschitz constant L. Possible looks at the differences between the most confusing rewards and the actual estimated rewards and favors arms where the sum of differences, weighted by their visit counts, is small. While Possible is able to consider the Lipschitz continuity of the reward function, it doesn't make use of estimated variances. Therefore, with insights from UCBV, we use estimated variances and derive Possible V. The augmented variance is used in Possible instead of the fixed variance. Otherwise, the algorithm stays unchanged. For evaluation, we use two complex traffic scenes in which interaction with other traffic participants are required. Collusions, by introducing an abrupt change in the reward, pose a counterexample on the underlying assumption in our work. For this purpose, we simulate the case of an imminent collusion. In the intersection scene, the ego vehicle has to identify whether other vehicles are on the colliding paths and, in case, has to avoid collisions. We define two scenarios based on the scene, which pose low and high probabilities of collusion respectively. If the transition model and reward function of the ego vehicle are Lipschitz continuous, the resulting Q-value function of a Markov decision process is guaranteed to be Lipschitz continuous as well. To expand this result to POMDPs, the observation function needs to be Lipschitz continuous as well. This is not the case in our model, as the reward includes the binary collision term, rendering the Q-value function discontinuous. We argue, however, that the noise which is present in the transition and observation model has a smoothing effect on these discontinuities. To highlight the discontinuity in the reward, we evaluate collision scenario without uncertainties. In this figure, you see the resulting Q-value profile. If the agent chooses an action between -2 and -0.2, a collusion cannot be prevented. Coarse and more accurate approximations of the Q-value profiles of the collusion scenario are presented in the next figure. The coarse one is approximated with 10,000 particles, whereas the more accurate one is obtained by sampling 10 million particles with 17 actions and a doubled resolution of the observation discretization. From the more accurate simulation, it can be seen that the variance is reduced. However, the Lipschitz continuity in the Q values starts to appear. This points out that the Lipschitz assumption loses its validity under low uncertainty. A standard metric to benchmark convergence is to identify the optimal action after a predefined number of samples. We use mean absolute error between the current best action and the optimal action as a performance measure. We calculate the optimal action by sampling 10 million particles while employing the UCB bandit. The observed Q values still have a stochastic nature, and hence we perform Gaussian process regression to eliminate the noise of the Q values and to recover the underlying function. We estimate the optimal action afterwards. The optimal Lipschitz constant required for Possible can also be obtained from the mean of the fitted Gaussian process. To perform a reliable convergence analysis, we calculate the mean average error over multiple simulation runs. We run the simulation 100 times to obtain this average. Given the ground truth, we determine the optimal action until an episode as an action that maximizes the Q-value function. We inspect the convergence results for the collusion scenario first. In this figure, you can see the results for 5 actions. The profile of UCB, UCBV are visualized in blue and light blue, whereas Possible and Possible V are visualized in red and orange respectively. Here we see that all bandits perform comparably. In case of 9 actions, Possible and Possible V begin to perform slightly better. This trend also applies to 17 actions. In case of 33 actions, the UCB bandit has twice the mean absolute error compared to Lipschitz bandits after 20,000 episodes. So these results indicate that as the number of actions increases, Possible and possible V show superior performance. In intersection scene, we inspect the scenario with high collision probability first. In the upcoming figures, we use the same color scheme we used before. In the figure on the right, you see the results for 9 available actions. We can see that possible and possible V perform better than UCV and UCBV. The performance improvements obtained by the utilization of Lipschitz assumption is already visible. In case of 17 actions, the performance improvements become more remarkable. Possible and possible V perform significantly better than their UCB counterparts. In case of 33 actions, UCB and UCBV fail to make any progress over increasing number of episodes and yield almost the same result. It's clearly visible that UCB bandits are incapable of handling that number of available actions, whereas possible and possible V show good convergence. The results are more interesting in the intersection scenario with low collision probability. Here on the right side, you see the result for 9 available actions. Possible performs better than possible V and also better than the UCB bandits. At the end, all the bandits can reach the optimum, but note that the action discretization is bigger for 9 actions than for 17 or 33 actions. In convergence figure of 17 actions, possible V starts to outperform possible. UCB and UCBV perform alike, but they perform worse than possible bandit. In case of 33 actions, strikingly, the possible bandit shows the slowest convergence, and the possible V performs the best. The poor performance of possible is caused by misleading rollouts which point to a different area of the action space to be optimal. The Lipschitz assumption causes the bandit to select actions in that area. By selecting actions with higher variances more often, possible V compensates the drawbacks resulting from such misleading rollouts. This scenario resembles such a narrow case in which the consideration of variances is advantageous. Tree depth of a solution is an important indicator of the quality. Deeper trees consider longer horizons and are more accurate. In this figure, we compare the tree depth for UCB and possible bandits for collusion scenario with the same number of particles. The bars in the figure represent the number of created nodes, and the color scales represent the number of visits for each level of the tree. It is clear that UCB has a greater branching factor compared to possible, resulting in shallower trees. This indicates that possible is in terms of tree quality better than the UCB. In our experiments, other scenarios have verified this result as well. In this work, we show 2 important results. Firstly, we show that uncertainties in transition and observation model have a smoothing effect on the discontinuities of Q values. This allows to make a Lipschitz continuity assumption on Q value profile. Secondly, we reveal that utilizing continuity of Q values allows significant performance improvements. We have further proposed the possible V bandit algorithm. The most remarkable feature of this bandit is its robustness against misleading rollouts. Real-time capability constraints have limited the use of existing POMDPs to decision-making problems with fewer actions. With this work, we are able to accelerate the speed of POMDPs with a novel tree expansion technique that exploits Q-value structure of our problem. This enables the use of POMDPs for problems where multiple actions need to be considered, such as in motion planning. Thanks for listening. Please feel free to drop me an email if you have any questions.